This is Ken Johnson for another episode of SecCast. This is the 5th episode in our Intro to Web Hacking series. In this tutorial, we will show some fundamental things to look for when attacking authentication-related functions. We won't discuss SQL injection or other more advanced techniques. Instead, we will focus on the controls surrounding some of these mechanisms. We'll discuss enumerating valid user accounts, demonstrate testing account lockout policies, and cover password complexity requirements. Additionally, we will attack forgot password functionality and demonstrate a vulnerable remember me function. Let's get started. Typically, username enumeration occurs because the application indicates whether or not a user exists on the system. This occurs most frequently at login, account updates, forgot password, and registration functions. The first thing we will do here is attempt to log in with a valid account on the system. We will provide an incorrect password and view the response. The application complains that the password is incorrect. This is very specific and right off the bat indicates the application might be vulnerable to username enumeration. Next, we are going to attempt to authenticate with an account that does not exist on the system. test78@test.com. The error message indicates that this user does not exist on the system. This demonstrates that bad passwords and bad usernames receive two separate notifications. This makes figuring out who exists on the system and who does not fairly easy for us. Next, let's try this exercise on the forgot password function. We will enter our invalid account of test78@test.com into the function. The error is a little bit more generic this time. At this point, the determination isn't clear. Let's try this with our valid account. In this instance, using a valid account triggers a different error message and redirects us to the login page. This means we can also use the forgot password function to enumerate valid accounts. The next thing we want to check is the account update page. We will attempt to change our email address to a user we know exists on the system and watch for the response. Now, you can see there's a failure message here, but this brings up a good point. Always check the raw response, as this might reveal a little bit more about what is going on under the hood. As you can see, we have been provided an incredibly verbose error message that indicates the user already exists on the system. This means we have another function that we can leverage to enumerate valid user accounts. Account lockout functionality is implemented to prevent guessing user passwords by trial and error. I'm going to demonstrate a quick way to check for the account lockout threshold. We'll first send a login request, intercept it, and send that request to intruder. Once at intruder, we will remove the auto-generated insertion points because we don't want to change this data. This request is fine the way it is. Keep in mind, this request has a correct user but incorrect password. It is important to strip your cookie or anything that is used as a session mechanism from the request. This is because developers often like to associate an invalid login counter to a session. If we remove the session, there is no way to track our failed login attempts. Again, this is if the developer has insecurely created their lockout mechanism. Next, we will choose a payload. Since we really don't want to tamper with the data at all, we will select null payloads and send the request 300 times. This means we will send 300 incorrect login attempts. Now, we kick off the attack. And you can see that 300 requests have completed. Let's navigate back to our original request, which is stuck in the Intercept tab, and change the password to the correct password of test. Once we allow the request through, we can see that we are still able to authenticate into the application. This means that the account lockout functionality either doesn't exist or has been created incorrectly. Password complexity requirements is a highly debated topic, and I will not attempt to give a definitive set of guidelines. However, we have provided you with a link under the references section of this tutorial to Dave Ferguson's blog, which has a decent set of baseline requirements. One thing that is clear is that you do not want a simple length restriction to be your only password requirement. This makes guessing passwords really easy. especially if the application does not have an account lockout mechanism and or user accounts are easily enumerated. So there really should be additional requirements that increase the difficulty level required to guess passwords. So we're going to walk through a few common places you'll want to check for password complexity, both its existence and that the password complexity requirements are uniform everywhere within the application. We'll start here at the sign-up page. You can see that when creating an account, the only requirement is to enter a 6-character password. Again, if your only requirement is a minimum password length, then the application's password controls are insufficient. Here, we will attempt to check the account's update page requirements, as this is another common area where we will see passwords being entered. We will attempt to use a form of the word password. In this instance, we are updating our password to password1. Most security experts agree that any form of the word password should not be included in a user's credentials. Lastly, we will change our account to that of an administrator. It is important when assessing the security control to do so anywhere a password is being updated, so never forget about administrative interfaces. In addition to ensuring requirements remain uniform everywhere within the application, the other thing we are going to test for is that a user's password value cannot be the same as the last several passwords the user used. In order to test this, we will change a user's password to password1. Since this is one of the user's last several passwords, this request should fail. Because it does not, the application has failed to check for this security control. Forgot password functionality usually falls into one of two categories. In-band occurs when you are able to reset your password or access your account without ever leaving the application. Out-of-band requires some secondary form of communication in order to complete this process, such as an email or SMS. The first thing we would like to demonstrate testing for is forgot password tokens sent via email. The first thing we are going to demonstrate is testing for entropy. The links that are emailed to us must be random. There are additional requirements which we will discuss later, but for now, we will focus on testing the randomness of these tokens. What you see here is our mailbox simulator. Currently, it is empty. We first want to send a forgot password request. Next, we will intercept that request and send it to intruder. Similar to the testing for account lockout section, we will remove the auto-generated insertion points, choose a null payload, and select 300 requests. In reality, you want to test at a minimum several thousand tokens. The larger the pool of values you are assessing, the greater the odds of finding a weakness in how tokens are generated. We can see that 300 requests have completed. Let's navigate back to our inbox. Next, we will randomly check a link for the token or values that are being sent and paste into Burp Suite's compare tool. We will repeat this process by once again randomly selecting one of the links sent to our account. Upon comparison, you can see that there are no differences between links. This usually indicates the value used to generate the token persists, so it is likely generated using a value that is specific to our account. Now, we've covered a very quick look at comparing two separate links with tokens in them, but this isn't helpful when trying to test the overall randomness of tokens that continuously rotate. For this, we will use Burp Suite Sequencer tool. This tool takes a large pool of values and analyzes them for how strong their randomness is. During an assessment, we typically use code to extract these values from each of the emails sent by the application. A link has been provided that demonstrates what this code looks like for Gmail. After collecting all of these tokens, we place them into a file named tokens.txt. Next, we navigate to Burp Sequencer tab, switch to Manual Load, and perform the analysis. You can see that our entropy has been given a rating of extremely poor with 0 bits of entropy. If entropy is not strong enough, these values are susceptible to automated guessing attacks. The next thing we want to test for is tampering with this token value. There are two parts to this token, and the first part appears to be comprised of our user ID. We will attempt to change this to the ID of the first user because often the first user has the most amount of privileges or is an administrative account. That did not work, so the account is not susceptible to tampering in this way. However, because the token does not change, we believe that it is made using a static value specific to our account. Additionally, it appears to follow the format of an MD5 hash. Let's tinker around a bit. The first thing we will do is load up IRB, which is Ruby's interpreter. It allows us to write code on the fly. We will first test hashing our own email address using the MD5 algorithm. Next, we will take this value and compare it to the token generated by the application. It appears we've discovered the logic used to create our tokens. Using the numerous instances of username enumeration vulnerabilities present within this application, we've determined that admin@metacorp.com is a valid email address. Let's try to hash this email address. We will take this hash value and place it into the token, as well as rotate the user ID to the number 1. It appears the application accepts this value. Next, let's try and reset the password. And we will attempt to authenticate, and we've successfully hacked the account. There are a couple more basic checks. You want to ensure that the forgot password token is deactivated upon it being used. This prevents reuse. Additionally, the token should expire within a reasonable period of time. And lastly, don't forget, analyze and tamper with this value if possible. When it comes to assessing security question functionality, there are some baseline questions you should be asking yourself. Is it possible to guess the security questions? Meaning, are there any anti-automation protections in place, such as CAPTCHA or request throttling? When I enter security answers, are they obfuscated the same way we obfuscate passwords? If not, it might be possible for someone to shoulder surf and view your answers. If an error occurs upon transmission, does the response render back the user's security answers within its response? If so, it may be cached in the user's browser. Are users allowed to define their own questions? I don't mean selecting from a list, but rather typing in the security question they will be asked. Researchers have found when this behavior is allowed, it can be detrimental as the questions are too easy or common. If this is a multi-step process where you enter in your email and are then presented with security questions and finally allowed to reset your password, is it possible to skip answering the security questions and go straight from step 1 to 3? Remember Me functionality allows the user to extend their session for greater periods of time. There are many things to check for here, but I wanted to show you an interesting issue we've seen occur on more than one occasion, although this manifestation differs slightly. We will attempt to authenticate with a non-administrative account. You can see we passed in the Remember Me option. In the response, we are given an auth token, which is our Remember Me cookie. First, we need to decode that value to remove URL decoding, and after having normalized the data, place into Burp's compare tool. This application has a feature that allows you to enter in your bank account number, and it provides an encrypted value. We believe the encryption routine used to generate this encrypted bank account number is the same function used to create a user's Remember Me cookie. Again, because we've determined that our Remember Me cookie does not change, we believe it is derived from a static value. We will enter our user ID into the bank account field. Let's take the value generated by the application and compare it with our Remember Me cookie. It appears we've discovered another encryption weakness. Now we will enter the number 1 for the user ID value of the administrative account on this system. Next, we will edit our cookie and URL encode special characters. Let's navigate to the dashboard. As you can see in the upper right-hand portion of the screen, we are now authenticated as an admin. Additionally, you can see on the left-hand sidebar that an admin icon is present. We've successfully broken the Remember Me functionality. To recap, we've learned about user enumeration, common authentication weaknesses, discussed token entropy, and demonstrated attacking a vulnerable Remember Me function. I'm Ken Johnson. This has been another episode of SecCast. Thanks for watching.